There we go, 1 o'clock. Welcome, everyone. Today we are going to have a licentiate seminar from Yali Nie, who comes from China originally and studied her master in South Korea, and then came here to the cold north and have been doing her PhD studies for about 2 years. Within the field of automatic melanoma detection that we will learn more about today. Also, we have with us, my name is Jan Lundgren, I am the main supervisor, and we on Zoom have Mattias and Nils, that is the co-supervisor. The English is eluding me today. Also on Zoom we have the opponent for today, and that is Klaus Lundstrom from University of Linköping. Claes, maybe you can say a few words about yourself?
Absolutely. Thank you for inviting me. I'm very happy to be here today. My background is did my PhD in medical visualization, and that's a track that I've been pursuing since that. I have actually 2 positions. I'm adjunct professor of Linköping University at a center called CMIV, and adjunct means that I also have another job, and that is in industry at a company called Sectra. So medical visualization is the key keyword for my research, but that entails a lot of things. And in recent years, I've been working a lot with AI for medical image analysis, and one of the things that I'm spending most of my time in is the national arena for AI and imaging diagnostics called ADA, that aims to join forces, that everybody in Sweden working with research and innovation in this area can join forces to make even further advances.
Thank you, Claes.
Thank you, Claes.
What will happen now is that we will hear the presentation from Yali, what she has done in her work, and then there will be a 10-minute break, and then we will have the discussion with the opponent. So for those of you joining on YouTube now, the broadcast will end after the presentation, but you can follow us on Zoom. After that, there will be a bit of a longer break where the supervisors and the opponent will have a discussion about the work, and then we will reconvene in, what will that be, 20-30 minutes, something? And we will announce the results. But first things first, we always start with the errata. That means that, is there anything that you have found in the thesis now afterwards, after it's been printed, that is some sort of error that changes the meaning of something?
Yes, there is one figure in page 12. There is the green, the words, it's wrong, it's training data. Page 12, so it's a little bit of mistake here. Yeah,
that's it.
And the paper 3, it's already accepted, and it is going to update, going to publish soon, I think. Yeah, before we finish the thesis, we just send it to the Melanoma 2021, and we haven't published it yet, but now it will publish it soon. Yeah.
Yeah, and we will be presented this summer, right?
Yeah. I think in June. In June we need to make a presentation.
Yeah. Okay. Some spelling errors. That is, if it's not worse than that, then I'm happy. So I will now leave the floor to Yali. You can start your presentation.
Okay. Hello everyone in the room and in Zoom. My name is Yali Nie. I'm a PhD student in Mid-Sweden University in Sundsvall. And 2 years ago, I started this journey towards becoming a doctor, and now I'm on halfway. So today I'm going to present you my licentiate thesis. It's called Automatic Melanoma Diagnosis in Dermoscopic Image based on Deep Learning System. First, I want to tell a little about what is melanoma. Maybe you will be a little wondering. Melanoma, it is one kind of skin cancer. Our final goal is try to design one application for the dermatologist to help them to distinguish the melanoma or not melanoma. The figure we can see here, it is our final goal. With a cheap and simple meloscope we attached with the phone, then you can acquire the images, upload it, then you will know something about the information from the images yourself. Maybe you even do not need to go to the hospital. So in this thesis, we have totally 4 parts. Now we are going to tell something about the introduction part. We have a problem with the skin cancer, it's melanoma. Melanoma, it is one kind of malignant tumor, and there are 17% of the skin cancer is related to death. And in 2019, there are more than 96,000 patients. They are newly diagnosed the melanoma, and more than 7,000 people they related to death. So it is a very serious problem. From this figure, we can see this world map. The most serious situation should be in US, Canada, and Australia, and New Zealand. Of course, here, this part, it should be the Europe. We care much about the Sweden. The Sweden, it is on the top 6 here. Every 100,000 people will have more than 23 people will get this skin cancer problem. And Australia, it is the first top. We have the problem in the current situation to diagnose the melanoma. Actually, there are more than 2,000 skin diseases are culturally known. On one hand, it is very challenging to diagnose. So around 50% of the diagnoses are incorrect if you go to a public hospital. And another thing is that the students, they don't have enough training in the university. They are very new with it. What's more, it will be very costly for the unnecessary weight or test. So sometimes if you give the error diagnosis, it will take more time and more money on it. From this figure, we can see 2015, the diagnosis, the dermatologists select from the Europe countries. We see here every 100,000 people, how many dermatologists are here. We see the Northern Europe has less dermatologists, but the Austria or Italy or Germany, they have more dermatologists than us. And in Norway, there is only 3.1 dermatologists. But in Australia, there is more than 9. In our research, we have this motivation for our research. The key to surviving melanoma is early detection. our aim is to diagnose the two based on the deep learning, and we want to try to develop the device to help the dermatologist, also some general practitioners, and also other physicians. So it will be easier for the patients to track on their the skin cancer or melanoma case, the different situation always. And what we want from the research, we want to design the design algorithm. It is faster and better to diagnose the melanoma. Of course, it should try to help the dermatologist to do fewer errors. And one more important thing is that to try to reduce the costs. We always meet these challenges when we try to do the melanoma classification, like hairs, the skin with hairs and gap bubbles, or the color chart. All the images will have this kind of noise there. They will make it difficult for the machine to learn the images. And this shows some more extreme difficult images. They are more challenging for no matter for the human or for the machine. So also they can be distributed everywhere, like the nails or back, neck, or foot. Everywhere it can be there. We are talking about the solution now. Then the methodology, it is in the second part. First, maybe we want to know something about how the machine learn or how the human learning. For the machine learning, the machine will learn from the melanoma and the melanoma both together. After they learn the database, they will get some knowledge on it. Then when you give it a new images, it will say it is melanoma or not melanoma. It will give you a diagnosis result. But for the clinician, the learning, he will try to see one image, and he will learn the name of the melanoma. He will remember some feature there. After several training years, after a few years, they will try to make it higher accuracy on a new case of the melanoma or not melanoma. We are going to use deep learning. It is one kind of artificial intelligence. For the artificial intelligence, we always say the computer power, algorithm, or data, they are the trick of the AI. But if we take the AI as one simple rocket, we can see the data, it is the fuel, and the algorithm should be the engine. And the computer power will be the accelerator. So the accelerator, we see the computer power, we always use some GPU thing. We see it is cheap, or it is very important for the artificial intelligence working. We want to compare a little bit about the CPU and GPU. If we say GPU, it is one powerful professor. Then he can handle very complex tasks. But the GPU, it has a big group of people, and they only do some repetitive and simple tasks. So for CPU, it only for the small model and small data set, it can work on it. But for GPU, it will work for the large models and the data set. We use it for image processing or video processing. It is more popular. Later, we will tell something about why we need the GPU, not the CPU. In our research, we have a little small directions, because for us, we try to use a smaller data set for melanoma classification. Because the big data set, some open source for the big data set, it already have a lot of work already have done. But some data set, the quality has a little problem. We find some label, it is wrong. You know, if for machine, if you tell it is some wrong thing, it will learn some wrong thing. So also another thing for the local national hospital to collect the data set, it will be a little difficult. Also manually to label some data set, it will take a long time. So if you have a lot of data set, it will be a big problem to, it will consume too much time for the data storage or for the expensive GPU, or both of them will be the problem when we do some research. So we have the smaller data set with high quality data. It will be very necessary for our research. Of course, classify the melanoma instantly and more precise always be our goal, because we can do it faster because we want to deploy it to the mobile device, so we want a light model to work on it. And we want to help the patient or help the dermatologist, so the accuracy it is must be must one necessary thing. We also talk a little about the coordinates for melanoma classification. In this figure, we can see the main parts will be the in between the input and the output. The input it is one images for the melanoma, and the output is a prediction. We classify it as melanoma or not melanoma. Between them, they are stacked with the convolution layer and the pooling layer, and in the end we follow one full connecting layer. We call all the convolution and pooling layer. We take them as a feature extra module. And the more convolution layer, it is try to extract the image features, and the pooling layer, it will try to reduce the dimensionality, and it will avoid the overfitting efficiently. And the output will try to do some classification. It is prepared for it. We tell a little about the pooling and the convolution. Maybe we are wondering how it works. For the convolution layer, they will, it is operated of cyclically multiplying the image with a feature element by element, and then summing them to about another feature map. After calculate all, then they will move the right and the down. So it will do it step by step. After all the work have been done, then a new feature map it will be there. And about the max pooling layer, of course we have the average pooling layer. For the max pooling layer, they are similar thing. But for the max pooling layer, we'll choose such as we choose one pooling, the size it is 2 by 2. We try to find the feature from the feature map. We find the biggest one, then we keep it. So we always try to keep the most important information from the feature. Here we show something about the supervised learning. We always try the supervised learning because it is more efficient for the classification, for the melanoma classification. The training samples, it should be the features plus the labeled data set together. Then we train it after training all the data set. We get one model. We use the new model, try to test some unlabeled data set. Then we get some new images. We find it is melanoma or not melanoma. It will do the diagnose work. In our small data set, we try to use a yellow detector. In this yellow detector, this system takes detection as one regression problem first. It divides the image to S by S. Always we can change it as best or 7 or 30 or any grades. And for each grade cell, it will predict a few bounding boxes. And there is one confidence score. Each cell also predicts 2 conditional class probability in our work. And we use the NMS diagram to retain the largest score. And finally, we had the bounding box of the melanoma here. And for the, we also did one work about the k-fold cross-validation. We worked it on the VGG16. We split the training data, all the data set as training and test, but the training will split the 5-fold. In our work, we use a 5-fold cross-validation. So the data set is randomly divided into 5 groups. Each time, one of the group is used to the test set, and the left K-1 groups will be used the training set for whole the training processing. And finally, we got 5 models. We examine the model and we test on the new data set. Another thing, we use 7-point checklist for our work too. And here, what is the 7-point checklist? It is one scoring diagnosis system. It simply adds the score of each criterion that is printed with the lesion. Like one images, it has some different features. We give it some score, then we add all the scores, simply add them together. If the score it is more than 3, we'll say it is melanoma. Otherwise, it is non-melanoma. And this algorithm is the best sensitive for the non-experts. Even you are not know something about the melanoma or non-melanoma, but if you follow this 7-point checklist, also you can tell that okay, yeah, maybe it has some problem with melanoma or non-melanoma. We combine this melanoma, the 10-point checklist with the convolution neural network. We make it one the classifier. It is one multitask. We use the 7-point checklist followed by the 3 convolutions, and it feels close to the design policy. We also use the majority design and then process as the vector X. According to the suitable logical model, we find the classification results about the melanoma or non-melanoma here. In our data set, we have 3 different data sets. For the yellow, we use 200 images from ISIC 2016, and we choose the full half benign and half malignant. And the key-fold, we use another data set, the data set from University of Salano and the University of Naples. It is less than 1,000 images. For 7-point checklist, we worked on one open source images. There are over than 1,000 images. Here we also tried 10-fold diagram here. Okay, now we are talk about our results here. From yellow, we get the results. We have 3 different versions of the yellow. We found that the yellow 2 have the best results on the object matrix here. Maybe we will see a little bit why the yellow 3 it has a little problem on it, because yellow 3 it is specialized in smaller object detection. Maybe that's the main problem here. That's why yellow 3 we didn't get a better performance than yellow 2. the results from the key fold, we have the file fold model. We have file fold cross validation, and we get the file models. That means that we have the 68% the accuracy on it. And we see here some images, they are very similar. Maybe this data set, it is from, it is not open source. We have it from the University of Salano. So some images look very spacious, not very easy to tell they are malignant or they are benign. This result is from the 7-point checklist. We try to use the accuracy and the sensitivity, also the specificity, the different metrics here. Because only accuracy, it is not enough to tell the model it is good or not good enough. Here we want to talk a little about more about the sensitive. It is much more important than specificity, because if we misdiagnose one patient, it will be very dangerous in the future. That's why we want a little higher the sensitivity than the specificity in the future. Okay, now it's the conclusion problem for us. We have reviewed the deep learning as our big potential application in dermatologists from the diagnose to treatment, and also we think about that it is very necessary to apply small data set to deep learning. And our future plan that we want to propose a more efficient network in the future, like the GAN model or the example model. We try the efficient network or the mobile network because they are ladder model, and they will be easier to deploy to the mobile device. And we see the 7-point checklist. It is very promising in the future for the multi-task learning models. We will continue with it. Maybe we also want to try for the challenging things. We want to reconstruct the data set. Like we will generate some new data set, remove some noise from the data set. Again, we want to deploy our model to mobile devices in the future. Yeah, okay. So that was everything from me, and thank you for listening. And I would love to answer all your questions. Thank you.
Thank you very much. Let's see, 2 meter distance, 2 meter distance. Here is good. Okay, thank you for a great presentation. I think it answered some of your questions maybe already. You will have the opportunity to ask questions after the opponent from the audience as well. I would like to take the opportunity also to tell you a little bit about, let's say, how the work has been done. It's been done within the Regional Development Fund project Digga Hälsocentral in collaboration with Region Västernorrland and Premicare that have looked at more a broader view on the next steps for digitalization of the healthcare system. And our parts have then been to look at strategies and implementation for automatic melanoma detection, among other things. So that this will hopefully be a natural part of the primary healthcare in the future, and also for a support for specialists. I also see in the Zoom room that we have some guests from Italy. You also did a short tour to Salerno. Salerno came up in the presentation here as well. I see we have Dr. Marco Caratu and Dr. Paolo Sommola in the Zoom room. Nearly did a tour of 3 months, I think, in Salerno. Yeah, a very good exchange. If we have some other PhD student listening, that's something to think about. Maybe a little bit of a visit abroad gave a lot of good collaborations, and we have had some co-publications as well. So it's a very fruitful collaboration. Thank you very much to you guys. With that, I think we end the YouTube stream. Thank you for listening. And we take a small break and continue on Zoom with the discussion. Thank you very much.